Hello everybody and welcome to this presentation. My name is Hassan Harkus and today I will talk about the performance-aware management of P4-based cloud environments. P4 is a programming language designed for programming packet processors. Using P4, we can describe the packet processing pipeline of different devices. The P4 language is target or device independent, meaning that the same P4 program can be used to configure different classes of P4 programmable devices, such as software switches, network processor units, FPGAs, or even ASIC switches. So there is no need to implement a new program for different devices. When we write a P4 program for a specific network functionality, this program will go through the P4 compiler to generate the bit stream or the configuration file that will be loaded to the P4 programmable device. This program can be a simple layer 2 forwarding network function, or it can be a more complex functionality such as VXLAN or so on. So you can imagine that when the P4 program is more complex and contains more operations, then this will result in a bigger configuration file that needs to be loaded to the device. So in case of software-based devices, there are more lines of code to be executed, and for hardware-based devices, this means that there is a more complex processing pipeline. In a previous work, our measurements revealed that when running the same P4 program on different P4 devices, the forwarding latency could vary by more than 12 folds, as in the case when running the program on FPGA switches versus running it on a software-based one. On the other hand, the measurements revealed that even on the same P4 device like Metronome SmartNIC, the forwarding latency could vary up to 85% when the complexity of the P4 program varies, as in the case when running layer 3 forwarding versus VXLAN decapsulation on the Metronome SmartNIC. This shows that selecting the right device for running a specific P4 program can make a big difference on the overall performance of environments built up from these P4 programmable devices. Accordingly, in this work, we optimized the placement of P4 programs into an environment made up of different types of P4 programmable devices, where we leverage the knowledge about the performance of these devices to achieve the best possible performance. We consider a scenario where a cloud environment made up of different types of P4 programmable packet processors is under planning. This environment should support processing an expected workload of network functions written as P4 programs. The optimization problem tries to find the optimal placement and the optimal set of processing P4 devices that could run this workload while achieving the best performance and cost. In our approach, we consider the requirements of P4 programs on one hand and the capabilities of P4 devices on the other hand in order to find the best matching placement. Let's look first what are these network function requirements. Each P4-based network function is made up of a set of P4 constructs or operations which when combined creates this function. The network function could also require some external functions such as encryption that should be on the hosting P4 device. Moreover, each network function has an expected throughput to be processed. And finally, the compatible P4 architecture for this network function should be specified among these requirements. On the other hand, each P4 device is defined by the following capabilities, and these include the maximum supported throughput on this device, that is its line rate, the base processing delay, which includes the delay of the non-P4 programmable blocks on this device, the processing delay of running different P4 constructs on this device. Moreover, the processing resources, whose definition depends on the type of the processing platform. For example, while processing resources are expressed in terms of available lookup tables in the case of FPGA, it's expressed in terms of number of stages in ASIC devices. So as a common ground, we decided to quantify the processing resources of a P4 device as the maximum number of P4 constructs that could run simultaneously on that device. The cost of the device represents the capital expenditure. Moreover, the P4 architecture which is supported by this device should be specified. And finally, the available external functions like encryption. So these available external functions on the P4 device should be specified, as well as the maximum throughput and the processing delay when running these external functions on this specific P4 device. The optimization problem should fulfill the following constraints. The placement should consider that the program should run on a compatible P4 architecture. Some network functions, like the layer 3 forwarding network function, must be placed on every used packet processor to guarantee proper packet forwarding between the devices. A hosting device should support all the external functions required by the network function. The processing capacity of the P4 device should never be exceeded, and this is checked by comparing the size of the P4 program to be placed on the device to the processing capacity of that device. The cumulative throughput required by different network functions to be placed on a device should never exceed the limited throughput of that device. And similarly, the cumulative throughput of network functions that require offloading some functionalities to an extern on a device should never exceed the limited throughput of that extern when running on this device. In this slide, we elaborate on the objective function of this optimization problem. This multi-objective function shown in this equation targets minimizing the weighted sum of the overall packet forwarding delay in the system and the overall capital expenditure. The weights mu and epsilon are used to tune the relative importance of each metric. Let's look first into this delay component. This overall delay is calculated as a summation of the delays of all network functions in the network. It's calculated as a summation of network functions delay over all network functions, device types, and instances of these devices. The Boolean decision variable alpha FDL is equal to 1 when network function F is placed on instance L of the P4 device of type D. So this P4 device type denotes like FPGA versus ASIC and so on. Delta FD, which denotes the delay of running a network function F on a device of type D, can be calculated as a summation of three components. The first one is the base processing delay of a function on a device of type D. The second component is the delay of processing different P4 constructs, which is the summation of the delays of each construct on this device, denoted by small delta CD, multiplied by its number of occurrences in this network function, which is denoted by sigma FC. The last component is the delay for executing the required external functions on this device of type D, and this is equal to the summation of all external delays, denoted by delta ED, if these externs are required by network function F. The overall capital expenditure, which is the second term in the objective function, is calculated as the sum of the prices of all the functioning devices in the network. And this is calculated as shown in the following equation, where the dependent variable xdl indicates whether the instance L of device of type D is being used. The parameters corresponding to the requirements of the network functions are surveyed from the literature and shown in this table. We consider 5 different network functions with different complexities. These are layer 2 forwarding, layer 3 forwarding, firewall functionality, and VXLAN decapsulation, and finally load balancer. The layer 3 forwarding network function is required to be in every functioning device to ensure proper packet forwarding between different packet processors. It's assumed that all network functions are required to process 1 gigabit per second traffic. All network functions are compatible with the 3 common P4 architectures these are V1 model, simple sum switch architecture, and portable switch architecture. And only the load balancer network function requires an external hashing function. Each network function is decomposed to its atomic P4 constructs with the methodology described in the referenced previous work. For example, layer 2 forwarding network function requires parsing and modifying a single header, which is Ethernet, while layer 3 forwarding requires the same operations for both Ethernet and IPv4 headers. Now we move to the parameters corresponding to devices capabilities. We select 4 types of P4 programmable packet processors, and these are CPU, MPU, FPGA, and ASIC based processing platforms. The capabilities of these considered devices are shown in this table. The first row shows the P4 architecture supported by these devices. The throughput values are based on measurements evaluated in this prior art. The maximum number of supported P4 constructs are based on the comparative analysis conducted in this prior art, which ranked the different devices based on the available resources. Since no work in literature gives a quantitative evaluation of the maximum number of supported P4 constructs on different P4 devices, we assume some reasonable numbers that follow the ranking provided by this reference paper in terms of available resources. The cost of different P4 devices is shown in this row. In general, we can observe that CPU-based processing is cheapest, followed by MPUs, then FPGAs, and finally ASIC devices. Note that the cost for CPU-based switches is assumed to be approximately equal to the price of 2 cores, as typical P4-based software switches run with this minimum requirement. The performance related to the external hash function on different P4 devices, which is needed by the load balancer network function, is extracted from this reference paper. And finally, the latency cost of different P4 constructs on different devices is surveyed from this paper. In general, we can observe that ASIC-based switches deliver the best performance in terms of latency, followed by FPGAs, followed by MPUs, and finally CPUs. We can observe that there is a trade-off between the cost of devices and the performance they can deliver. And note that there is no evaluation in the literature that quantifies the variation of latency on ASIC devices as a function of the P4 constructs and P4 externs. So in this work, it's assumed that the ASIC-based devices are powerful enough to run any P4 program without latency variation and to execute a hashing function with performance higher than the other device types. The next step is to evaluate the proposed model. For this purpose, we consider again the 4 network functions described in the previous slide, as well as the 4 types of P4 programmable devices. In this evaluation, the workload is varied as multiples of the previously defined network functions, from 1 to around 200 network functions. The objective is to find the optimal placement of these network functions, as well as the set of P4 devices to be used to suffice this placement. The optimization problem is solved using the widely used Gurubi solver. 4 scenarios are considered in this evaluation, where mu and epsilon in the previously defined objective function are varied. In scenario 1, the objective is to achieve the best performance disregarding cost. In scenario 2, we look for the cheapest solution where the best effort performance is sufficient. In scenario 3, the objective is to find a balanced solution where both performance and costs are equally weighted. Finally, in scenario 4, we look for the solution that brings the best performance, but for a predefined constraint on the cost so that it does not exceed $100,000. This figure shows the optimal placement solution after running the optimization. The x-axis of this heat map shows the increasing number of network functions to be placed. The y-axis shows the number of instances needed from the different types of P4 devices. These P4 devices are ASIC, FPGA, MPU, and CPU-based devices. The color goes to red when the number of required instances of these devices increases. The optimal solution for scenario 1, where we look for the best performance, is trivial, where all network functions are placed on ASIC-based devices, as these are the most performant ones. For the maximum workload of 218 network functions, 15 devices are needed. On the other hand, the cheapest devices, which are CPU-based, are selected in scenario 2 to place all network functions when the objective is only to minimize costs. In this case, 25 CPU-based devices are needed to place all the network functions. In the third scenario, the MPU-based devices accomplish the best trade-off between performance and costs, where 22 network processor unit devices are needed to place all the network functions. More interestingly is scenario 4, where we look for the best performance for a predefined cost limit of $100,000. In this case, it could be observed that for low workload, one ASIC device is selected as it provides the best performance while still being affordable given the limited cost limit. Recall that the price of an ASIC-based device is equal to $40,000. Then another ASIC device is utilized when up to 22 network functions need to be placed, where the second device is needed because the processing resources constraint is reached on the first device. In this case, the cost raised to $80,000. After this point, no more ASIC devices could be used as the remaining $20,000 budget allows only for the second best performance device, that is FPGA. In this case, up to 4 FPGA devices are needed to process the additional network functions until reaching 90 network functions. After this point, one ASIC device is sacrificed to enable affording more FPGA devices that could support running the higher workload. At 174 network functions, the second ASIC device is also substituted with more FPGAs until reaching 20 FPGAs when the number of network functions reaches 200 network functions. Finally, the optimal solution further sacrifices performance where it starts substituting FPGA devices with the next best performant device, that is MPUs, so that it can support processing all network functions with the provided budget. In this figure, the delay function corresponding to the optimal solution in microseconds as a function of the number of network functions to be placed is plotted in a logarithmic scale for different scenarios. This other figure plots the cost objective function in dollars. Looking at scenario 1, where the target was to maximize performance by minimizing the delay, we can see that the overall delay is minimal while the overall cost is the highest. On the contrary, when looking to scenario 2, where the target was to minimize costs, we can see that the overall delay is the highest while the overall cost is the smallest. Results corresponding to scenario 3 show the trade-off between the two objectives, where the overall delay and cost are equally minimized. The results of scenario 4 show that the delay of the system is as low as that of scenario 1 when only the delay is optimized, until the budget constraint is reached after 22 network functions. After this point, the delay of the system starts increasing compared to scenario 1, while the cost is always less than the preset budget of $100,000. To wrap up, here we summarize the main takeaways of this talk. The placement problem of P4 network functions in a cloud environment is studied. The placement decision targets optimizing the forwarding delay in the system as well as the cost. To guarantee the highest possible processing performance, we build the problem formulation on top of prior art that maps the atomic P4 operations to the corresponding processing delay on different P4 devices. We conduct numerical evaluations to showcase how the provided mathematical formulation can assess the planning of P4-based cloud environments with minimal forwarding delay and costs. This evaluation showed the trade-off between these two objectives. In future work, the model could be extended by considering service function chains embedding that could be distributed across different devices and subject to latency and cost constraints. Additionally, an experimental testbed could also be built to validate the effectiveness of the proposed optimization model. Moreover, the runtime management of the P4 environment with dynamic workload requests could be further investigated. And this brings us to the end of this talk. I would like to thank you for your attention, and I'm glad to answer your questions.